All right. Thank you very much, in particular Fred and Alex, for putting this event together. It's really nice to be here in person at the Collège de France. So yeah, I am Jonas Landman, PhD student at the Université de Paris with Jordanis Kernidis. And I am going to talk about quantum machine learning. So what is quantum machine learning? It's the question we ask. It's if one day we have this fault-tolerant and universal quantum computer, will we be able to perform some machine learning task? So machine learning is quite important nowadays, and we want to find quantum algorithm that solves some quantum machine learning problems, such as classification, clustering, and many more, in fact, but you might know about it. The other question we ask is, can we find some quantum algorithm with provable guarantees? We want to control over some parameters. For instance, the quantum effect. There is randomness occurring during measurement. There is a low precision due to the limited number of qubits, and so on. And we want to compare the guarantee of a quantum algorithm to the classical machine learning, that they are supposed to be equivalent. So we can say if using a quantum computer is useful in some aspect, such as the speed up or some other advantage like the accuracy and so on. So let's take a first step back and look at the foundation of quantum algorithm. If you have followed Frédéric Magniez lecture the past few months, you may know about it. But quantum machine learning algorithms are built upon these foundations. So we have quantum Fourier transform, we have phase estimation, amplitude estimation, and many more. I mean, you don't have to know about them for the rest, but it's good to know. And we have the first blocks to solve a linear algebra problem, such as matrix multiplication and inversion since 2009 with the HHL algorithm, and some other stuff regarding more spectral decomposition, eigenvalues, singular values, and so on. What we have been trying to do is to build new middle ground tools that enhance in linear algebra, so quantum algorithm to perform an inner product or distance estimation between vectors. So this is important, that we can derive to become a convolution product. In the graph theory, we can extract some information about the spectral embedding, the spectral, many properties, and many more. But I'm going to focus on these. And at the end, the goal is to develop quantum algorithm on some end-to-end classical machine learning that are equivalent to some end-to-end classical machine learning algorithm. And I'm going to present a few of them, right? Not all of them. It includes some clustering algorithms, so k-means and spectral clustering. And on the left here, you can see more neural network things. So, but I will go into the details later. So in terms of the foundation of quantum machine learning, it all boils down to linear algebra. And it's a good news that machine learning is speaking linear algebra language, and we know that quantum physics is also speaking linear algebra language. So the first question we need to ask is, if we want an algorithm that takes classical data, right, from an experiment or from everyday life, and want to perform some computation and output a classical result, we need to interface classical data and quantum state, because these are processed by quantum circuits, okay? So a way of doing so, I guess this is not the only way, but a good way to do it is to use amplitude encoding. So if I have a vector x of dimension d, the idea is to use a state in a superposition of many states j here, and I want that the amplitude of each state, I want them to be the component of my vector d, right? So my vector x, sorry, which has d component, right? x1 up to xd. So there are two ways to do the amplitude encoding, at least. The most efficient one is the computational basis, where you only have log d qubits, and on each binary combination of this log d qubit, and you have d of them, you would put the component as the amplitude, right? And you are very careful, and you make the vector to be of norm 1, so that the amplitude squared sum to 1, of course. The other way you can do is to use unary basis. Instead of using log d qubit, you only use d qubit, and you put the amplitude only on unary state, which means that it's state that have only one qubit in state 1. Okay, so next, there is the other way around. So imagine at the end of my quantum algorithm, I have a quantum state that is supposed to represent the answer, the result of my computation that is unknown, and I want a classical description of it, because I'm a classical being. The idea is to retrieve the classical description of the vector by making multiple measurements and estimating these amplitudes. This is pretty difficult, in fact. You have to perform many measurements, and this is always done with some approximation, right? So you see an epsilon in the number of measurements you have to do. And there are several ways to do tomography, but we'll speak about it later. So it's very important. A very important result is the fact that we can perform linear algebra operation faster using quantum computers with this specific type of encoding. In particular, we can compare the distance between two vectors, noted x, y, and xj, for instance. I have these two vectors, and I want to calculate the distance. So the idea here is that I put a first step in the metric or the topology of my data, and you can feel that this is what gives the power to machine learning, right? Know which data are similar, and so on. The circuit is pretty simple. The idea is to, given the ability of loading this vector in the amplitude encoding, you just have to apply a Hadamard gate, and then the probability or the amplitude of some state is actually proportional to your inner product, and then you have to do the amplitude estimation. I don't want to go too much into details. We might talk about it later. So finally, another important subroutine is matrix multiplication. I mean, this is pretty well known since 2009, but it has been improved so far. I don't want, again, to go into the details, but you should notice that in the running times, so the big O notation, you see weird parameters. So these weird parameters are eta, or mu, or kappa. You also see the epsilon, which is just the fact that you have some precision, some approximation. And but the eta, the mu, and the kappa, they refer to some data-dependent parameter. So in my running time, it depends on actually the value itself, which is not very common in classical machine learning. It means that if you have a vector that has high values, the algorithm could be slower than if it has small values. So it's pretty weird. And for mu and kappa, it means that if you have a low-rank matrix or a sparse matrix, the running time can be different. All right, so let's see a first quantum algorithm for machine learning. There is a famous classical algorithm called the k-means, and the goal is to solve the clustering task. So what is clustering? It's pretty simple. You have points in space. You can imagine a high-dimensional space, and you assume that they are distributed among clusters, and you want to automatically find these clusters. So it's an iterative algorithm, right? And the loop is as follows. So you have the black points that you want to, that are, VI, and you would start by randomly initializing centroids. And the centroid is what you expect to be the center of your clusters. So they are random. And what you will do is that for each data point and for each centroid, you will compute the distance. So you can imagine that you have to do this a lot of time, right? Then you will select the shortest distance. And simply you would say, I will assign the label to this point, being in the cluster red in that case. So you have a first label assignment for each point, but you can see how wrong this is. But it is an iterative algorithm, so you will repeat that loop. But before, you will move the centroid, because they have been initialized randomly, and you move them to be the new average of the current red cluster. And then you repeat that loop until you find the good cluster. So in this case, it's pretty easy, because it's quite simple. And so what we have done recently is to propose a quantum version of this iterative algorithm, which we call the q-means, of course. And the idea is it follows the same step. So at the difference that instead of computing the distance between each vector and the centroid, we would start in a superposition of all vectors. And this is very efficient because we have this distance estimation procedure that I showed you before, which allow me to compute the distance in superposition over all points. Then, again, don't want to go too much into the details, but the idea is that once I have this distance, I can compute the minimum one, again in parallel or in superposition, and select the label and so on. So it's actually the same thing. but I try to keep coherence and not to destroy my quantum state during the computation. At the end, we have to perform automography to retrieve the centroids, but remember that there is only k, or here, 3 centroids, and not all of them. And during this step, we use all these routines, such as quantum access to data, inner product and distance estimation, matrix multiplication, and tomography. In terms of runtime, so it's logarithmic in the number of points big N, whereas the classic algorithm is linear, because you have to compute distance for each point. I'm giving you a simplified runtime here, in particular for well-clusterable datasets, meaning that the points are, the clusters are well separable like this. And you see a delta parameter appearing here. It is actually showing the precision. So delta is a precision parameter because, again, in quantum algorithm, everything is a bit approximate. So we had to simulate this algorithm and see if this delta parameter was important. So first we saw that compared to the red curve, that is the classical algorithm, the quantum k-means was able to learn. So what you see, the x-axis is the number of iterations, and the y-axis is the accuracy. So I need to improve my clustering. So for high value of delta, we are still learning, so it's quite a good news. So this is learned on a data set made of images, handwritten digits, and the algorithm must learn how to read them. Later on, this algorithm has been generalized to Gaussian mixture models. The idea of this is that instead of having spheres of high dimension, I can have Gaussian blobs. So not only I have to find the center, the centroid, but also the covariance matrix, right, that is giving me the shape of my blobs. All right, let's try another algorithm, which is called spectral clustering. So the idea of spectral clustering is, again, to separate and distinguish data. But the difference is that it is able to classify much, let's say, complex shape of clusters that are nested sometimes. And you can see that on the left, the k-means algorithm fails to classify them. So the spectral clustering is very interesting because the power comes from graph theory. I find it very interesting. The idea is to first compute a similarity graph where you can see the graph correspond to the data and 2 points are connected if they are close. So again, we see this idea of distance, which is very important. And from this graph, we can compute something called the Laplacian matrix, which is quite common in graph theory. So this Laplacian matrix actually have size n by n, where n is the number of points. And we will compute the eigenvectors and eigenvalue of this Laplacian matrix. And then we will select like the lowest eigenvalues and the corresponding eigenvectors. This will define a basis, so a new space on which we will project our data. And by some dark magic, the points in that space are well clusterable due to the topology and the connection within the graph. So in that space, I can actually apply k-means, the first algorithm, and then I go back to the initial space, and I have distinguished the two data. The main drawback of this spectral clustering algorithm is the running time, which is cubic in the number of points big N, because actually when you have to deal with eigenvectors, eigenvalues, spectral decomposition, it's pretty long, classically. And you can see, again on this little demo, that for instance, on the moon, on the 2 moons here, it takes 1.5 minutes, which is very long compared to the k-means. So again, we have proposed a quantum algorithm to solve spectral clustering. It's pretty straightforward, I think. We compute all the distance, again, it's always the same now, in superposition. So we have access to the graph, and then we use pre-existing tools from our group to extract eigenvalues, singular values, in fact, but it uses a bit like phase estimation, if you know a bit this algorithm. And then we can separate somehow naturally the low eigenvalues and the high eigenvalues and project onto that space. And at the end, when we are into this subspace with low eigenvectors, we can use q-means, so the previously developed quantum algorithm, to find the new centroids. So we have made some simple numerical simulation. So you see the two graphs here, on the classical on the top and quantum on the bottom. They are kind of similar, but you see that quantum is a bit different. I mean, because when we estimate the distance has some noise around it, right? We don't estimate stuff perfectly. But the good news is that in the spectral space, so we have projected into the two lowest eigenvectors, you see that the projection is different, but in both cases, you could distinguish and you have well-separable clusters. So at the end, we are able to classify these two concentric circles with the quantum algorithm pretty good. So we wanted to see in this simulation if we could retrieve like the running times, the complexity. So we did have this cubic growth for the classical algorithm when we increased the number of points. And for the quantum case, we saw this linear growth, which is already a great improvement. And this is actually the worst case predicted by the theory. OK, so that was unsupervised learning or clustering. Now let's move to some neural networks. So, OK, neural networks, they are quite well known nowadays. But I mean, I think they are kind of, yeah, it is inspired by the way our neurons are connected in the brain. But I mean, whatever. For me, it's just a series of matrix multiplication. And between each matrix multiplication, there is a nonlinearity. So a layer, like the black wires here, are all matrices, here written W. And if I have an input X here of dimension 4, I will apply a series of matrix multiplication until the end. So here the output is of 2 dimensions. The output is supposed to be the exact result, so I can tell if my neural network is giving good result or not, so I can compute an error. And I want this error to decrease while I change the weights of my matrices W during what we call backpropagation. So backpropagation is that I have to compute the gradient of my weights according to the error I make at every step, and I want to decrease this error by changing the weights. More formally, if you look at, for instance, the first element of my first hidden layer Y, it is actually the inner product between my inputs, X, and the first row of the matrix W here. So again, inner product, I'm very happy because I know how to do it. But the important thing is that we also have to apply a nonlinear function, f here. And nonlinear, when you do quantum circuit, you're not happy, because actually when you apply quantum circuit, these are unitary matrices, which are linear by nature. But a group proposed a way of performing this neural network very efficiently, again using this inner product estimation that I have showed you before. Again, you have to load the input vector and the weights in superposition, and you can apply this matrix multiplication kind of faster. Now, we can apply the nonlinearity as well, because when you do the inner product estimation or the distance estimation, right, you write the inner product value in a register. So it's now written in binary, so you can apply a Boolean circuit of a nonlinear Boolean circuit if you want. And there is kind of the similar construction for the backpropagation. And you can show that this goes faster than the classical algorithm. So now let's look at a recent work on convolutional neural network, which is a more evolved type of neural network. These are used everywhere nowadays, I think. It's especially for image, for sound, for video, everything that involves, I guess, signal. And it's pretty interesting. They have replaced matrix multiplication that I showed you before by convolution product with the input and some kernel, as we say. Again, this is, I guess, inspired by the visual cortex and the way your brain deals with image in our eyes. So what is a convolution product? Simply, if you have an image here, the convolution product with a small kernel gives this kind of output. You can see it as a pattern detector, right? The kernel is scanning the image, and here, for instance, it's detecting edges. But you need to remember that the most general framework is actually to use tensors and not matrices as input, because you usually have colors, right? So it's red, green, blue, and so on. But let's say that the general setting is to use tensor. So we have to define a tensor convolution product first, All right, don't worry. The idea is that your kernel is now a little tensor as well, and it's pretty simple. You take the little tensor, you put it on the first subregion, you perform an inner product, and then this gives you one value, right? It's the inner product. Then when you would shift it to the next region, it gives you another value, and so on. So at the end, what you just need to know is that a convolution product like this gives you a matrix at the end. But if you want a tensor, because we only deal with tensor, then you have to use multiple kernels. So, okay, maybe it's a bit lot, but you have a 4-dimensional kernel and a 3-dimensional input. This gives a 3-dimensional output. So this replaces the matrix multiplication. This is one layer, okay? And after you will again apply nonlinearity and some other stuff. So we have proposed a quantum algorithm version of this. Again, here a bit simplified, but the idea is always the same. If we can rewrite a convolution product as an inner product, there is a bit of technical details, but you just have to load this image or these kernels in superposition quantumly. Once you have access to the amplitude encoding, you can perform this inner product estimation. So you obtain this matrix Y. Then you have to reshape it as a tensor, but actually when you have quantum state, it doesn't really matter. And then, yes, you apply the nonlinearity F and so on. But at the end, what you have is only a quantum state, right? It's not a classical state. Also, the same applies for the backpropagation. So then when you have a quantum state at the end, you need to perform a tomography. And as I said, tomography can be very costly. If your dimension of the vector you want to retrieve is of dimension d, sometimes it can cost time d, in fact, if you want to have a norm 2 precision guarantee. But what we have been doing is propose a new type of tomography called the L-infinite tomography because it uses the norm infinite norm. So it's a it's a loose tomography. I mean, you make more mistake, and it's probable that you will not see small amplitude. And here, epsilon is the error you make. But a very interesting thing is that this loose tomography, which we would not like a priori, is very well suited for this neural network, because in neural networks, not all information is equivalent. Some pixels in your image or in your output, they contain meaningful information, like the high-value pixel. These are the ones you use to tear apart a 5 from a 6, for instance. And if the other thing is that usually when you use the nonlinearity, you put points apart, like small value points are even smaller and high value points are even bigger. So I mean, we did some experiment to show that this L-infinite tomography was enough in the context of neural network. Then at the end, we performed a full quantum convolutional neural networks. Was pretty interesting. So we can compare the learning curve with the black one, which is the classical convolution neural network. So here you see the training curve. It means that you have the number of iterations at the bottom. Iteration is each time I will update the weights, or I will update these little kernels. And you see the loss function or the error. So you want it to decrease maximum. And you see that if you use quantum convolutional neural networks, it can learn for different value of sigma. So sigma being here the ratio, the amount of measurement I do compared to the size of the dimension. So you see that if I only take a look at 50% of my image using quantum tomography, it's pretty interesting to see that the algorithm is still able to learn. And the less I see in the image, for instance, 20% or 10%, I can still learn, but it takes a bit more time, as you can see. Even with 10%, it will start to learn a bit later. I don't know why. All right, so let's take a look at a final quantum neural network one, which is quite different, because this one is suited for NISQ, so noisy intermediate scale quantum computers, and it's called orthogonal neural networks. So what is an orthogonal neural network? Actually, you just take this fully connected neural network that we saw earlier, and you want it to be, you want each matrix to be orthogonal, meaning that each rows are orthogonal vectors between each other. And this gives special properties to the neural network. For instance, some consideration when the neural network becomes very deep, some gradients become better for the training and so on. So what we have proposed in a very recent work that actually was put on the archive 3 days ago is a quantum circuit that is very small, that is not using all these previous tools that we showed before, like phase estimation and so on. It's just this inverted pyramid here. And this is actually implementing any orthogonal matrix you want. Well, it's pretty obvious at first, because any quantum circuit is a unitary matrix, and if it has only real values, then it's orthogonal by default. And it uses this, each little vertical bar here are gates. These gates are called reconfigurable beam splitter, so RBS. And these are parameterized by an angle theta. So it looks like a kind of a rotation between the two qubits. Often this gate is native on some quantum computers, such as I think the Google Sycamore chip, or maybe on some maybe photonic platform one day. But if not, you can also decompose it into a small combination of Hadamard gates, rotation Y, and some CZ. So if you have an orthogonal layer with n input and n output, this is actually a matrix W with n square element, but it has only, in fact, n times n minus 1 over 2 free parameters because of the orthogonality. And you can see that this orthogonal circuit has as well n minus 1 over 2 free parameters. So the difference between the previous algorithm that I showed you is that this one uses the unary encoding, meaning that if my input x has dimension d, it has to have d qubits. And what I claim is that at the end, given one matrix W, I can choose the angle such that the output state is the result of the matrix product with my orthogonal matrix W. The good thing about this unary encoding is that, in fact, you can load it pretty easily using what we call the data loader. So it's actually, again, using this RBS gate. You do this little cascade with new angles, alpha 0, alpha 1, and so on, that are derived from the components of x 0, and so on. And it's pretty simple, and you see that it fits very well inside the pyramid, so it doesn't increase the depth too much, only by 1. And you start almost from the ground state. And finally, the good thing about this pyramid is that you can branch them as you would branch the layers of a neural network. So you have a very modular setting. And if you look at the first, after each layer, you would perform this kind of loose tomography or L-infinite tomography, apply a nonlinearity, and you would sequentially apply the layers. So we may wonder if this is interesting. Well, first, in theory, the classical, what you see here, the classical orthogonal neural network takes n square time per layer, okay? Because it's actually a matrix multiplication by a n by n matrix. But the quantum pyramid here is only depth n, which is the depth of the pyramid. So we have a quadratic speedup here. The fun thing about it is that while trying to simulate classically this quantum circuit, because this is only made of small rotation, we were able to propose a classical algorithm that seems to scale better, well, a bit better, which is n minus 1 over 2 in the forward pass, right? So to apply one orthogonal matrix product. In the backpropagation, it's a bit similar. So in fact, classically, it's a bit difficult to do the backpropagation. So again, backpropagation means I want to compute the gradient of each weight, so each black lines, and then perform gradient descent. It's difficult, but you need to, because you need to maintain this orthogonality, which requires some spectral decomposition or singular value decomposition. But classically, we made something that may make it a bit faster, so n square on the quantum and the classical case. Then we did some simulation. So you can see in red the simulation of the pyramidal circuit. You can see that it trains. So now it's the other way around. Okay, it's not going down, it's going up. And the blue lines is the classical one. Again, on this data set of handwritten digits, so small images. And finally, we have been able to implement this quantum pyramid on actual quantum computer, which is nice, using a 16-qubit device from IBM. It was a bit noisy, but still we were able to compare the simulation and the actual quantum computer results. They were close, unless you start to do some bigger experiments. And when I say bigger, it's not that big. Okay, these are very small stuff. But still, it was very interesting to actually implement a quantum circuit. So yeah, maybe it's time to conclude. Apart from the last part that I showed you, these pyramids, these were all long-term quantum machine learning algorithms. We wanted to answer some question. If I have a universal and fault-tolerant quantum computers, I will be able to do some quantum machine learning. So we use this traditional computer science approach. We have proofs, we have theorem, and we want to know really in theory if it's worth something. And we have provable guarantee in terms of noise and etc. And so the good thing about it is that it allows us to compare with the classical algorithm. And that's very important. So at the end, we can conclude that yes, maybe there are some quantum algorithm that could speed up, for instance, machine learning algorithm. And in particular, I think when it comes to heavy linear algebra procedure, when you have to deal with eigenvectors to spectral decomposition and so on. You also have seen the importance of data loading. I think this is very crucial to notice that we need actually data loading to interface classical world and quantum computation. And the good surprise, I would say, about this research is that at the end, you could also inspire a NISQ algorithm, so for near-term device. It's a good news. And you can also inspire classical algorithm, as we have shown in the last part, but in a more general way. It's pretty interesting. All right, that's it for me. Thank you very much.